Okay, chemistry section 2.2 part 9 now. Today's focus is going to be on what is called balancing of equations. And it is super important if you are choosing to go on to chemistry 11 next year. So to start off, we're going to talk about the law of conservation of mass in chemical change, which is something you should be familiar with. So a bit of a refresher. First off, I'm just going to have you take a moment and look at the two scales. So one says start, one says end, or a mass, provided on both of them. So basically this is showing coal being burned under a glass cover. So what do you notice between the measurements of these two scales? So I'm going to give you a minute, pause if you need to. So you should see that before and after the reaction, the mass is still 100 grams. So you can see that the coal has been visually reduced in size to ash, but the mass is still the same because the trapped gases and water vapor from the combustion reaction, which is the type of reaction, are still contained within that space. So mass is conserved from start to end. This was a principle put forward by Lavoisier in 1743 to 1794, so that was his lifespan. So the law of conservation of mass is super important. This is one of the fundamental laws of nature. So it states that matter cannot be created or destroyed, it can only change form. So that is basically what is summarized in the bottom here. This is again another example of what is called a combustion reaction. We'll get into that later. But wood is being burnt in oxygen. So the mass of the wood and the oxygen together will yield the same mass as the ash and CO2 and water that is produced from the burning of that reaction. So the volume will change because gas and liquid are involved, but the mass itself will remain the same. So mass in is equal to mass out, therefore matter is conserved. So this connects to balancing of chemical equations. So the mass of our reactants must equal to what it produces, which is called the product. So our reactants are what we put into the reaction. The product is what comes out after the reaction. So the materials we start with, which is what we're adding to the reaction, are called our reactants. What is produced is called the products. So here is an example of two diatomic gases coming together, so hydrogen gas and oxygen gas. Remember your diatomics and your special 7? So they're coming together to produce water. So there are a few different ways to represent reactions. On this slide, we see two of those ways. So one of them being a word equation and the other being what is called a symbolic equation. So let's break this down into some important points. Looking at the symbolic equation, so this is the bottom of the two reactions, this is what is a balanced chemical equation. So we can see that there are these numbers in front of the compound. These are what are called coefficients. So same as in math, when you have a number in front of like an algebraic statement, that is called a coefficient. So it indicates the ratio of the compounds consumed or produced in the reaction. So putting this in simple terms, if we were to focus on the 2NO, this means you have 2 molecules of nitrogen monoxide. And that means if you look at the atom level within this compound, we have 2 nitrogen atoms and 2 oxygen atoms. More to come on this. The little letters below tell us the state of the molecule. So you can see all 3 of these have a little G in brackets. So letters indicate the state of each compound. AQ is the newest one. Solid, liquid, and gas should all be familiar to you, remembering that we symbolize a liquid with a cursive L, not a line L, to make sure it doesn't get mixed up with a 1. Aqueous refers to something being dissolved in water. So this is going to come up a lot with our acids. The word equation is exactly as it is kind of written there. This is what you should be kind of the most familiar with thus far. So basically we are just naming these compounds and writing them out as their full name. So The equation below would be nitrogen monoxide plus oxygen yields or produces nitrogen dioxide. So it's as if I'm speaking out or reading what those formula are telling me. Okay, so a summary of the law of conservation of mass is in your notes. So chemical change means new compounds are created. No new matter is created or destroyed. Atoms are just rearranged. So matter can only be rearranged or transformed. All matter in the reactants must equal the matter of the products. So just like our wood burning example. Thinking back to early atomic theory, we had John Dalton and his billiard ball model of the atom. He recognized that atoms can only rearrange themselves during reactions. But he didn't bring it quite as far enough to reach the law of conservation of mass, which again states that all matter of the reactants must equal the matter of the products. So the number of each atom in the reactants equals to the number of atoms in the products. So for example, if we look at our picture at the bottom, which is methane, CH4, reacting with oxygen, producing CO2, so carbon dioxide and water. If you were to actually count out each color of atom, you would see there. For example, carbon is shown in gray. We see only one gray on either side. So you can see that when we count the atoms themselves, the reactants versus the products, you have the same number of atoms present when the equation is balanced. So again, these coefficients are what show us that our equation has been balanced. So the law of conservation of mass, to summarize, in chemical reactions, atoms are neither created nor destroyed. They can only be transformed or rearranged. This law was developed by Antoine and Marie-Anne Lavoisier in the 1700s. The mass of the reactants is equal to the mass of the products. So what does this mean for real life? If we have a car, for example, you know that gasoline is burnt. And if you were to collect and measure all the exhaust from your car, you would find that the mass of the reactants, which is gas plus oxygen gas, will equal the mass of the products, the exhaust. So writing out and balancing chemical equations. So the simplest form of a chemical equation is a word equation. There's no numbers involved in it, it's strictly the names of the compounds. So for example, potassium metal plus oxygen gas yields or produces, that's what this arrow symbolizes here, potassium oxide. So you can think of that yield symbol as an equals sign in math. So we have one thing plus another thing will equal something else. So this is all a word equation tells us. So the words describe what is going into the reaction and what is produced by the reaction. The next step up from this is what we call a skeleton equation. So this shows the formulas of the elements and compounds. The skeleton equation shows us the atoms, but it doesn't show us the quantities of the atoms, meaning that the skeleton equation is not balanced out. So if we're looking at our example, if you look on the reactant side, if we were to kind of split this reaction in half, you'll notice that we only see one K, where on the product side, we have two of them. So looking at this, this is not a balanced equation. So potassium we symbolize as K. Oxygen is diatomic. Remember your Hoberfinkel acronym to help you remember this. So oxygen always exists as O2 gas in nature. So when these two things react, it produces K2O, which is potassium oxide. And again, we represent produces or yields with that arrow symbol. So we can count the atoms, as in we can say on the reactant side, I have one potassium and two oxygen, but this doesn't tell us the total quantities of atoms in the reaction. In order to do that, we would need to balance the equation. So the last step is the balanced equation. So it shows all the atoms and how many atoms overall are involved in the reaction. The same number of atoms going into the reaction must be the same as what's going out of the reaction. So balancing ensures that the number of each atoms is the same on both sides of the reaction arrow. A balanced chemical equation we can think of like a recipe for a reaction. In chemical terms here, if we look at the reaction below, so 4K plus 1O2 yields 2K2O. The same amount of potassium is going into the reaction will equal the same amount of the product on the other side. We always use the smallest whole number ratio. So this is just like ionic compounds where you need to reduce, always where possible. So for example, looking at 8K plus 2O2 produces 4K2O. All of the coefficients, which are these big numbers, are divisible, meaning that they can be divided by 2. And if we were to divide all those coefficients by 2, we would end up with this, which is the correct form. So we would write the reduced form as our final answer, not the one that is doubled, the bottom one. So anytime you are able to divide by a common denominator, always do. To balance, we count atoms. So you have to look at things at the atom level rather than as the full compound. We have a word equation. Methane plus oxygen yields or produces water plus carbon dioxide. The skeleton equation, methane is CH4 plus O2 as oxygen exists as the diatomic, produces H2O plus CO2. So right now, this skeleton equation is not balanced. So we're going to kind of break this down so that you will hopefully understand how this balancing process works. So this equation, I'm going to represent with a bunch of pictures. So same reaction, we have methane, we have oxygen reacting to produce water and carbon dioxide. The bunch of arrows basically show us the produces line. So if we count up all the atoms on the reactant side, which is on the left side of my line here, I have 1 carbon, I have 4 hydrogen, and I have 4 oxygen, symbolized in red. On the product side, I still only have 1 carbon. Hydrogens, I have 4, and oxygens, I also have 4. So this is pre-balanced for you, but it's to give you a visual that the number of atoms going into the reaction must equal to the number of atoms going out of the reaction at the end once we have balanced it. So to balance the compounds, take note of how many atoms of each element occur on each side of the reaction arrow. If it helps, draw a line to split the two in half to help you keep track of it. You can also label reactants versus products, anything that will help you here. One important thing to know is that we do not write the coefficient 1. So if I go back to this example here, we would not want to include that 1 in our final balanced equation, because by saying O2, it means we have 1 molecule of O2. It's not multiple. So kind of like we don't write the 1 as subscript, same idea. So we use coefficients to add atoms, never, ever, 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 ever change the subscript. Okay, so coefficient again is the big number in front of our formulae for each compound. If we change the subscript, say from CH4 here to CH6, this would be something totally different. These aren't the same thing. It would no longer be methane, which would then change the entire reaction. So never change the subscript. Never. Okay, only add big numbers, which are coefficient, to change quantities. CH4 plus O2 yields water and CO2. So I'm going to start off with my carbon. So I have 1 letter C because there's no coefficient beside either of them. On my reactant side, I have 4 hydrogen, and I have 2 oxygen. When you are dealing with hydrocarbons, which are, as the name says, they contain carbon and hydrogen, we always balance the oxygens last. So that was what the meme was at the beginning. If you balance oxygen first, you're going to have a bad time because it will screw up the entire balancing process. So leave oxygen till last. On this side, we have 1 carbon as well. The hydrogens, there are 2 of them. And now if we look at oxygen, we have 2 here and 1 here. So that's a total of 3. Okay, so as of right now, our carbons are already balanced. So we're going to move on to balancing our hydrogens. Right now we have 2 hydrogens on the product side and 4 on the reactant side. So we're going to basically times it by 2. So 2 times 2 is 4 hydrogens. So now we have 4. But with that, we have doubled our oxygen. So we now have this 2 basically applies to the hydrogen as well as the oxygen. So 2 times 1 is 2, and then we again have this 2. So that gives us a total of 4 oxygen. So it's very much like math and when a number is in front of a bracket, for example. So now looking at our oxygens, we have 2 on the reactant side, but 4 on the product side. So we're going to stick a 2 in front of the O2 here, and this will make it 4. And then we just want to check. So I still only have 1 carbon. I have 4 hydrogen on the reactant side. I have 2 times 2, which is 4 oxygen. So that's done. On the product side, I have 1 carbon still. There's no coefficient in front, no subscript. Hydrogen from water is 2 times the subscript of 2, which gives us a total of 4 hydrogen. And oxygen, we have the 2 in front of water, which applies to that O. So 2 times 1 is 2, plus the 2 attached to CO2, giving us a total of 4 oxygen. So there is our overall balanced equation. So this is a slightly, it's not a hard example, but it's not the easiest example either. So I'm going to walk you through a couple examples from easy going through up to kind of more complicated examples. Okay, so 3 examples I'm going to go through with you step by step here. So our first reaction, we have iron, metal, and bromine gas reacting to produce iron 3 bromide. So step 1, we want to list out our different types of atoms on the reactants and the product side. So I'm going to draw my line to kind of split this down the middle here. So atoms on the reactant side, I have iron and I have bromine. And then on the product side, I also have iron and bromine. We're going to now add in our numbers for these. So on the reactant side, I only have 1 iron, but I have, from the subscript, I have 2 bromines. For iron on the product side, I only have 1. There's no subscript there. And bromine, I have a 3 based on the subscript. So these are our starting number of atoms that we have. This is not balanced. So we want to start from our first atom, which is iron in this case, and it's already balanced. So we're then going to move on to the next, which is bromine. We're going to consider the common multiple between these two. Always the lowest common multiple, otherwise you're going to end up having to reduce. So 2 and 3, the common multiple is 6. So I'm going to add a 3 in front of bromine, which would mean 2 times 3, which gives us 6. For our bromine on the product side, I already have 3, so to make that into 6, I want to multiply the compound by 2. So again, we end up with 6. So now our bromines are balanced, but if we look back, we now have 2 iron. So this isn't balanced. So we need to add in a 2 in front of the iron, so 2 times 1, you end up with 2. Appears balanced as of now, but we're just going to do a small check. We have 2 iron from the equation. 3 times 2 gives us 6 bromine, so that's good. I'm just going to write check above this so you know exactly what I have here. I can't fit it in. Oh, I should maybe check. There we go. 2 times the subscript of 1. Again, we have 2 iron on the product side. And 2 times the subscript of 3 gives us 6. So this is now balanced. So that top equation there is our final balanced reaction. Second example is getting a little bit more tricky. So we have tin for nitrate reacting with potassium phosphate, so that's a polyatomic, producing potassium nitrate and tin for phosphate. So just like before, we want to list out all of our possible different elements that are involved in this. I'm going to split my reactants and products up. Okay, so I have tin, I have potassium, I have nitrogen, phosphorus, and oxygen, if I look at all the different types on the reactant side. On the product side, I also have tin, remembering oxygen always goes last. This is a lot of different elements to deal with. So there is a trick with this, and there's a note here. This only applies if the polyatomic is the same on both sides. So for example, if we look at NO2, we have NO2 on the reactants and NO2 on the products. Same with phosphate, PO4. So identical on either side. So if they appear on both, making sure that there's no subscripts that have been changed, they must match perfectly. The outer bracket one is fine, that can be different, but the PO4 part should be exactly the same. Then you can treat it as a single unit. Also good to notice that I have tin and potassium first. So you always want to list your metals first when they are present. Okay, so let's start balancing this. Hopefully it's going to be a little bit easier now that we have kept those polyatomics together. So currently on our reactant side, I have 1 tin. Potassium I have 3 of. For my nitrate, which is NO2, I have 4 of them, indicated by this little subscript right there. PO4, my phosphate, I have 1, because there's no brackets and no extra subscript. On the product side, I have 3 tin, 1 potassium, 1 nitrate, and 4 phosphate, so 4 PO4. Alrighty, so now if we look, our tins are not balanced, so we are going to start with that. So I'm going to add a 3 in front of my tin on the reactant side, changing this to 3. So now tin is balanced, but that is going to change our nitrate. So we always then do what's attached to the tin. So my nitrate has gone from 4 of them up to 4 times 3, which is 12. Okay, so just by making that change to the tin, it's also changed the nitrate. So we're going to move to balancing our nitrate on the reactant side. So in order to have 12 of them, I need a coefficient of 12. So this is going to make our nitrate 12 as well as our potassium 12. Okay, tin is still balanced. Now our potassium is out of balance. So I need to make the 3 potassium that we have on the reactant side into 12. Our lowest common multiple would be 3 times 4 would give us 12. this is multiplied by 4, making it 12. But in turn, we now have 4 PO4s. And that works out really nicely because we already had 4 PO4s on the product side. So this, as of now, appears balanced. We're going to go through and double check and make sure everything works based on the reaction. So we're going to do our check. We have 3 tins. NO2, we have 4 of them initially, but 4 times 3 gives us 12. For potassium, we had 3, but we're multiplying that by 4, so again, we get 12. And then we had 1 PO4 together, 1 unit, so 4 times 1 is, we have 4 of them now. Okay, check on the products. We have 3 tin, so that's good, just based on the subscript. Potassium, we have 12 times 1, which is 12. For our nitrate, we had 1. We multiply that 1 by 12, we get 12. And for the phosphate, we had 4 of them initially, and we still have 4 because there's no coefficient. So those numbers all match. So this is our correct balanced formula. Okay, the last example is the hardest one to solve, and this is a hydrocarbon reaction. So also called, or sorry, not a hydrocarbon reaction. It has a hydrocarbon. The reaction type is called a combustion. So it's combustion of a hydrocarbon, which is an example of an organic molecule. So this is ethane plus oxygen, which is diatomic, produces carbon dioxide and water. So we're going to start off same as our other reactions. I'm going to split it down the middle and start listing my molecules with oxygen last. So I've got a carbon, I've got hydrogen, and I've got oxygen. Same thing on the product side. I have carbon, I have hydrogen, I have oxygen. Now we want to figure out our quantities. So on the reactant side, the subscript tells me I have 2 carbons, I have 6 hydrogens, and I have 2 oxygens. On the product side, I have 1 carbon, there's no subscript. I have 2 hydrogen, and then for our oxygen, I have 2 here and 1 here, so a total of 3 oxygen. Okay, so we are going to start with the carbon, then leave the hydrogen and oxygen till the end with the hydrocarbon, okay? So in this case, our products have less carbon, so we only have 1, so we need to double this. We're going to make it a 2, meaning that this 1 becomes a 2. Okay, by doubling that carbon, we also double the oxygen. So this CO2 molecule, there are 2 oxygens, so 2 times 2 is 4, plus this 1 again, so we end up with 5 oxygen. Now we're going to move on to balancing the hydrogens. So on my reactant side, I have 6, but on my product side, I have 2. So in order to make that hydrogen on the product side a 6, I'm going to multiply it by 3, meaning that this becomes 6. And our oxygen is again is going to change. So 2 times 2 from the CO2 is 4. 3 times 1 is 3. So we have a total of 7 oxygens now. So as of this moment, carbons are balanced, hydrogens are balanced. But our oxygen on the reactant side is 2, and we have 7 on the product side. So there isn't a whole number that we can multiply our oxygens by to make it balance. It always needs to be a whole number. So to get around this, we are going to double everything. This tends to happen when the oxygens are an odd number. Sometimes you can fix it without doubling everything, but when in doubt, you can double everything. Just check at the end to make sure you don't need to reduce. I'm going to do my doubling in a step-by-step manner. Again, leaving the individual oxygen till last, but we're going to start with carbon. So I'm going to change this into a 4. So now instead of 2 carbon, we have 4 carbon. And then that in turn is going to change my oxygen, but I'm going to leave that for a second because I need to double my first carbon, which is also a 2. So this becomes a 4. Okay, next I'm going to go on to my hydrogens and double those as well. So I'm going to change this to a 6. I'm leaving the oxygens till last because we have to sum them up in order to make the comparison back to the individual oxygen molecule. So this is just to make the balancing easier. So by changing that H2O to a 6, I now have 6 times 2, so I have 12 hydrogens on this side. And this one was already 12. I just forgot to change that. Sorry. So 2 times 6 from this coefficient also makes it 12. For our oxygens now, we are going to sum up what we have on the product side. So we have 4 times 2 from the CO2 is 8, and then 8 plus 6 gives us 14. So this is exactly what we want. We want it to be an even number because we have this, anything we put in front of that oxygen is going to double. It's going to be an even value. So now, looking between 2 and 14, if we multiply this O2 by 7, we end up with 14 of them, which then balances the reaction. So with these hydrocarbon combustion reactions, there is a little tiny bit of trial and error, but also just remembering that you need to leave the oxygen till last because it can really mess things up. What we want to do now is look at the overall reaction. So we have 2CH2H6, we have 7O2, we have 4CO2, and we have 6H2O. None of those have a common denominator. We can't divide them by the same thing, so that's good. We don't need to reduce, but we do want to now check and make sure everything is balanced properly. So I'm going to do my little check here. Coefficient of 2 times the subscript of 2 on carbon gives us 4. The coefficient of 2 times the subscript of 6 on hydrogen gives us 12. And then the 7 times the 2 on the O2 molecule in the reactants gives us 14. Same with our products. We have a 4 in front of the CO2, so that is a 4 for carbon because there's no subscript. There's a 6 in front of the hydrogen. 6 times 2 with the subscript is 12. And then last, we're going to do our oxygens. So 4 times 2 on CO2 is 8. 6 times 1 is 6. 6 plus 8 gives us a total of 14. So this balances. It's always a good idea to make your balanced formula look nice in the end. So if you've crossed things out and things like that, I'm going to rewrite it as 2C2H6 plus 7O2 yields 4CO2 plus 6H2O. Okay, so those are all balanced. You will have lots of practice with this. And like I said, the combustion reactions tend to be the most challenging. So extra practice with those is always a good idea. So everything is all balanced with these. That's awesome. We've checked our work. Also great. So always remember to check at the end. Okay, so we're going to do one more example that shows a reduction reaction. So just to really make sure you understand the concept of a reduction. So this isn't in your notes, but feel free to add it in. Writing out my components of each compound. First, I want to point out we have the polyatomic nitrate on the reactant side, but we have NO2 nitrite on the product side. So because we don't have NO3 on both sides, we must break that polyatomic up into nitrogen and oxygen. You cannot keep it as a polyatomic because these are two different ions. Listing my reactants, I have potassium, I have nitrogen, and I have oxygen. Again, oxygen always last. Splitting this down the middle, we're going to add in and count our molecules. So I have 1 potassium on the reactant side, 1 nitrogen, and 3 oxygen. On my product side, I have 1 potassium, 1 nitrogen, and then I have 2 oxygen from the potassium nitrate and 2 from the oxygen gas, so giving us a total of 4. So add those subscripts together. So from here, to start off, balancing our oxygens, because on one side we have 3 and one side we have 4, we're going to attempt to kind of make this the common multiple, so that's 12. So I'm going to start by multiplying the potassium nitrate by 4. So that's going to bring us up to 4 for nitrogen, and then to 12 for oxygen. And then for our KNO2, I'm going to multiply this by 4 as well, because we've got a 2 from the additional oxygen, so we're going to try and make our oxygens as close to 12 as we can. We obviously are going to have to adjust this. So 4 nitrogen, 4 O2 is going to be 8 plus 2, which gives us 10. Double our oxygen. Now, here, this will bring us up to a total of, so if we do our checks with these, before that, we're going to notice here that I have 4, 4, and 2. All of these are divisible by 2, therefore they need to be reduced. So we're going to divide everything by 2, and that's going to become a 1. And now with that, we can do our final checks to make sure everything balances. So we're going to have 2 potassium, 2 nitrogen, oxygen is going to be 6, and then 2 potassium, 2 nitrogen, and 2 times 2 is 4. 4 plus 2 gives us 6. So this balances. I'm just going to write out the formula at the bottom. So 2 KNO3 breaks down into 2 KNO2 plus O2. So notice I haven't written the 1 in because it's, by just saying O2, it means we have 1 of them. Hints to writing word equations. So word equations require careful examination to be written correctly. So make sure all of your compounds are written down properly. The chemical symbol is used for most elements present in a compound. Be careful of diatomics and polyatomic elements such as O2, P4, and S8. So for phosphorus and sulfur in nature, they're unique. Phosphorus will appear as P4 in order to be stable, and sulfur will appear as S8. So 8, a group of 8 essentially bonded together. O2 is a diatomic. Remember your Hover-Finkel elements. So it is stable as O2 gas in nature. So again, these special 7 molecules, use the acronym to help you. You are required to know them. A few more hints. Several common covalent molecules contain hydrogen and have common names that you need to know. So for example, methane you're going to come across a lot. That's CH4. Glucose, you'll remember from cellular respiration. We're showing it to you again, C6H12O6. Ethane is C2H6. Ammonia, NH3. And then, of course, water is another one that is essential to know, H2O. Strategies for balancing equations follow these steps. Trial and error will work, but can be very inefficient and time-consuming. So it is an option, but try and follow the rules and it will help you to balance faster. Always balance compounds first and elements last. So HCl, for example, we're going to try to balance before the lone magnesium that's by itself. Balance one element at a time. So start at H2 in this example, then do O2 after. So we balance H2 on both sides, then move on to the oxygen. Only add coefficients, never change the subscripts. So the example here, I've got a coefficient 5 in front of H2. Never all of a sudden change the H2 to a H3. That is a massive no. Never, 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 never change the subscripts. If H and O appear in more than one place, attempt to balance them last. For example, HNO3 breaking down to HNO2 plus O2, we would balance the nitrogen first and then the hydrogen and oxygen. Polyatomic ions such as sulfate can be balanced as a whole unit if they appear on both sides of the reaction. So here we see SO4, and on the product side we also see SO4. If that subscript is different, they are not the same, you must balance them separately. So balance the sulfur, then the oxygen, and you must break it up. Always, always, always double check after you think you are finished. Make sure everything balances. And each time you balance an element, the next element you should balance is the one that's attached to the previous element. So if you balance carbon in methane, for example, CH4, you should balance the hydrogen that is attached to it that's attached to the carbon before moving on to the oxygen. So some more practice in your notes for you to do. Like I said, this stuff works out to be very much like a puzzle that you're solving. You're trying to make one side equal to the other side, and it's a lot of back and forth. So the more you practice it, the more you'll start to see patterns, the more it will make sense. If you are having any trouble with this, please reach out to me right away. Do not leave it, do not wait. This does confuse a lot of students, so you're not alone. Please ask questions and I'm happy to help you. So message me on Teams if you need anything. The more practice with this stuff, as I said, the better. It will definitely show up on quizzes and tests, so it's nice if you've perhaps seen the formula before, the equation before. So please complete your practice and then you can move on to your other assignments based on the schedule.